Just a quick introduction to the mechanics. The first section is looking at the types of graph. We've got three sorts of graph that we need to look at. The first one is the displacement time. Now, we talk about displacement because it's the distance from a point, and it can actually describe a situation where something goes away. So we've got displacement, which is equivalent to distance, but it's a vectored quantity because it has a definite direction as well. So if I was coming back from the tree towards the house, my displacement would still be the same as if I was going out. So at this point A, when I get to A both ways, it doesn't matter which direction I'm going in, my displacement is the same. So on the way out, my displacement to A would be this 3 kilometers. On the way back, I go through it here, and that's still the same displacement of 3 kilometers. On distance, we'll come on to y distance in a minute, but the distance from point B, anything where we're sloping downwards, the distance graph would probably slope the opposite direction, would do the mirror image. So my distance graph describes a better description of the distance travelled. So A on the way out, fine, I'm getting further away from the house, and then I get to 5 kilometers, and I'm further 2 kilometers. So this describes, I set off a bit fast, got a little bit tired about 3 kilometers, slowed down a bit and did the last 2 kilometers to the tree in the same time as it took me first. So these are each 15 minutes. That's at 30 minutes, and that's at 45 minutes, and that's 5 kilometers. On the way back, the distance travelled though doesn't start decreasing, it increases at the same rate. So in the last 3 kilometers we get back and we wind up with our position here. Well, I wind up back at home. So the distance graph actually would show, doesn't worry about the direction I'm moving in, it's just how far have you covered. The displacement graph shows where I am relative to the house. So it shows me coming back. Okay. So let's have a look at what we can say about places. Well, if I do the gradient of this line, or ds dt, is going to be the vertical distance, 3 kilometers, divided by 15 minutes, which is 1/5 of a kilometre per minute. It's not a usual unit. We normally use this in terms of parts of an hour. So this is a quarter of an hour. That means I'm doing about 12 kilometres per hour. So 3 kilometres in 0.25 of an hour. It's kilometres, and that would tell me I've got 12 kilometres per hour. Now, looking at that gradient and recognising this, you should recognise that as a speed. But because it has direction, we have a velocity. So at the moment it's positive because it's going away. So section A, we have either 1/5 of a kilometre per minute or 12 kilometres per hour. So the gradient of the line actually shows me my velocity or speed. Section B, do the same thing. I have speed going out. So let's call that VA. That's 12 kilometers per hour. Let's do the same thing for VB. So VB is the distance covered in the time frame for B. And this time it was only 2 kilometers. Again, in a quarter of an hour. And that will give me a final velocity of 8 kilometers per hour for VB. And then the journey home, C coming home, we now actually do a reverse distance of 5 kilometers for 25.25 of an hour, and that gives me minus 20 kilometers per hour. So that's actually quite useful in that I can now see the speeds I was doing. The problem people often have is they think, oh, well, if I just add these up, that will tell me my speed overall. Well, I've gone nowhere. So overall, we would have a velocity of no distance in 45 minutes, or 0.75. And that's no kilometers per hour. It's telling me I haven't gone anywhere. The second graph, though, what we can do with it is we can actually calculate the average speed. Now, the average speed, some people might actually say, I'm just putting the modulus around this. Some people might say the average speed is going to be VA, VB, and VC, all added together, which gives me a total of 40, and that was 40 over 3, which is 13 and 1/3 kilometers per hour. The problem is that they're assuming everything's equal. Now, that is actually the case in this one, I think. No, it's not. The actual average speed we did is the 10 kilometers in this time. So the average speed needs to take into account how far were we going in total, which is 10 kilometers. How long did it take for us to get there? 0.75, which gives me the same 13 and 1/3 kilometers per hour. Now, the reason that these two agree is these time frames were equal. If this journey back had taken me longer, then these average speeds wouldn't just sum up. So this is a peculiar case because each time frame is the same. Right, so that shows us one thing we can show. Let's take the displacement calculation graph, and we'll go on to the other graphs. It's too long really anyway. Let's put in my velocity. So the velocity we now know is what happens when we change speed. So I now have a velocity axis that can do this. Don't worry about the negative direction. But what we now can calculate is, for the first 15 minutes, I did a velocity of 12 kilometers per hour. Let's go for the 12 kilometers an hour. So 10, 20, 10, 20. So this is now our velocity in each phase. And my first velocity, we started off at the constant velocity. So all the way through here, the velocity is the same. Next section, it went down to 8 kilometers an hour. And the last section, we did 20 kilometers an hour. So that's 15 minutes, 30 minutes, 45 minutes. Now, if you think about the relationship, And we just did a form of differentiation, ds dt, and that gave me my velocity. If I want to go the other way, I can get s is the integration of velocity with respect to time. And we recognise this as an area formula. So what it's actually telling us is, if I take my 12 kilometres per hour, which is 1/5, that's a quarter of an hour. The area of this section is going to be a quarter of 12 kilometres an hour, which is 3 kilometres. The area in here is the 3 kilometres. The area in here, 8 kilometres for a quarter of an hour. Quarter of 8 is 2 kilometres. And my journey back, I've got a minus 20 times 0.25 gives me minus 5 kilometres. So the area under a VT graph is the velocity, is the distance covered. The question is, what's the slope of this telling me? Well, this one doesn't tell me very much. And the reason it doesn't tell me very much is my acceleration graph is the gradient of the line at various points through the graph. So the acceleration is, what's the gradient? So acceleration is, how does velocity vary with time? And by the same amount, if I come back, I can therefore say that velocity is the area under an acceleration graph. This is based upon constants. So what happens here is the gradient on this one is actually 0 all the way through there. Then it changes negatively very quickly, but then doesn't change again. Changes very quickly to become negative again and doesn't change. That's the effect of instantaneous change and constant acceleration. Is you will see these horizontal lines. Let's try taking a graph with the other way around. So let's take a constant acceleration graph and we'll apply some knowledge to it. So let's assume we've got an acceleration of 2 meters. Velocity is per second. So velocity by time is seconds squared. This is acceleration, and we're saying it's a constant. And this is the situation we find ourselves in for nearly every question in M1. We only ever talk about constant acceleration problems, or it being constant for a period of time. So to create a velocity graph, we've got A is 2, so V is the area under that. So it's 2t. Notice we can also have a constant. So this constant could be a starting velocity. So for my velocity graph, I could actually have a starting velocity and it goes up. So if I have a starting velocity here of 4 meters per second, and we say this is 1 second intervals. So if I start at 4, I gain 2 meters per second every second. A sloping line with a gradient of 2. And this first C is our starting velocity, normally denoted by U, is 4 meters per second. Okay? So we actually get told a piece of information, and now we can say my velocity is going to be 2 times the time plus my starting velocity of 4 meters per second. Let's take it again and go on, take the velocity, and we're now going to do displacement, 2t plus 4 dt, and again a displacement could have some fixed value it starts at. So if I start my displacement back here at minus 4 meters, my calculation for S is going to be 2t squared divided by 2, add on 4t, add on some constant, and the constant is my starting velocity position, minus 4. So when I put in the values, 1, that cancels out, so I've got 1 plus 4 minus 4 gives me 1 meter. If I put in 2, we've got 4, 8, that's 12, 8. And go 3, we've got 9, 12, 21 minus 4 is 17, which is just up here. And what you should see is we get a graph where there's a slight curve, and it's a parabola. Constant acceleration means distance changes with a parabola shape, not straight. All right, so that's the introduction to the graphs, applying our knowledge from P3 and P4 to allow us to calculate areas. So the area under an acceleration graph is the velocity. Area under a velocity graph is the displacement. If you differentiate displacement, you get velocity. Differentiate velocity, you get acceleration.